hi everyone. Welcome to our Q&A session today. My name is Travis Rector. I'm a professor of physics and astronomy at the University of Alaska in Anchorage. And I'm also one of the co-organizers for a group called Astronomers for Planet Earth. And our guest today is Dr. David Helfand from Columbia University. And this is the Q&A session for a talk that he recorded previously. So if you are seeing this recorded on YouTube, there will be a link below that you can go and watch his original talk. So David, thank you for joining us today. I just wanted to say first off that David is one of my personal heroes. He was one of the people who helped me to get more engaged in climate change many years ago. And David and I go way back, and I'll just mention that I found this in my pantry the other day. It's a little faded, but it is one of the original First Survey coffee mugs that David was one of the co-PIs on. So it's a little faded, but it still works just fine for its intended purpose. So that's how David and I first met each other many years ago. So for the Q&A session, the way we're going to handle this is that we have questions that were submitted by viewers of the video on YouTube. And also for those of you who are joined in with us, don't hesitate to jump in if you have any questions or comments as we go along. Probably the best way to handle it is if you have a question that you'd like for David to answer, you can just type it into the chat. But we have a pretty small group so far, so it's also, I think, fine for people just to unmute their microphone and ask questions as we go. I'd like to keep this more conversational than just a rote answering of questions. And so David, in your talk, you did a wonderful job of explaining the evidence that we have that establishes undisputedly that that the carbon dioxide that's being added to the atmosphere is of fossil fuel origin. And one of the questions we had on YouTube was wondering if you could just maybe briefly discuss the connection between carbon dioxide and rising temperature. Now, this is kind of climate science 101, but I think it would be helpful for people to know a little bit more about that. So maybe we should start with that question.
Sure, and I took the opportunity from that question to do a little further research myself and found a very curious fact. The first connection between a warming Earth and carbon dioxide in the atmosphere was actually proposed in 1856, so this is not new science, by a person named Eunice Foote, yes, a woman scientist. And her father's name, and I'm not making this up, was Isaac Newton Jr. No connection to the original Isaac Newton, I believe, because he was from Goshen, Connecticut, but nonetheless, her maiden name was Newton. And she did an experiment by taking glass jars and filling them with air in one case, water vapor in another case, and carbon dioxide in another case, and put them in the sun, and had thermometers in them, and found that the carbon dioxide one heated up much more than the other two, from which she concluded that the carbon dioxide was absorbing the sunlight and somehow keeping that energy. A few years later, John Tyndall, who is a Brit, reproduced this with a slightly more sophisticated way and recognized that it was the infrared radiation, not the visible light radiation, that was causing this warming. In 1896, Arrhenius published a paper that actually predicted our use of fossil fuels would lead to a warming climate. And so this is not a new concept. The way it works is this: the sun emits light that peaks at about 500 nanometers, or what we see as yellow light, because it's at a temperature of 5,800 degrees. The temperature of a body determines completely what range of wavelengths of light it will emit. And our atmosphere is completely transparent to light around 500 nanometers. And so the sunlight coming into our atmosphere passes completely through, unscathed. The Earth radiates an equal amount of energy back into space, because if it didn't, we just get hotter and hotter and hotter like an oven without a thermostat. But since the Earth, fortunately, is not 5,800 degrees, but more like 289 degrees on the Kelvin scale, or 20 degrees centigrade, it radiates at 20 times longer wavelength at something like 10,000 nanometers rather than 500 nanometers. And the radiation attempting to escape from the surface of the Earth back out into space is blocked by molecules such as water vapor, carbon dioxide, methane, nitric oxide, and various other molecules like that, that absorb radiation at that wavelength. Now, when they absorb that radiation, they destroy the photons that we're trying to leave, but that puts them in an excited state, and they don't want to be in an excited state, so they relax back to a ground state and re-emit radiation. But they re-emit it isotropically, which means it goes in all directions, and half of it goes back towards the Earth. So it produces exactly the same effect that when you're lying in bed at night in the winter and you're cold, your body is radiating infrared radiation. And since it continues to do that, you get colder and colder until you pull on a blanket, which blocks the infrared radiation and radiates it back towards you, making a nice, cuddly, warm little cocoon inside your bed. And so that's what's happening to the Earth. And it's a very good thing, because without the greenhouse gases that provide this blanket, the average temperature of the globe would be -5 degrees centigrade, or about 21 degrees Fahrenheit, which means most of the globe would be frozen and maybe life never would have evolved. So the greenhouse gases are a good thing on Earth, but just like if you pull 5 blankets on you in the bed at night, you wake up in a sweat an hour later, too much greenhouse gases is a bad thing. And so it's a balance that has changed over the lifetime of the Earth, naturally through natural processes, but currently is changing very rapidly because of our use of fossil fuels.
That's great. I learned also recently that Joseph Fourier in 1820, I believe, was the first to calculate that the Earth was hotter than it should have been, just based on the amount of energy coming from the sun. And he speculated that it had to do something with the atmosphere, but he didn't know why. And then I think Eunice was the first to figure out that it was greenhouse gases were doing that. So this year actually marks, and that's from that perspective, I think this year marks the 200th anniversary of us knowing about the greenhouse effect in some capacity. So I think that's a really important point to emphasize when we teach climate change and talk with people about it. This isn't something that just, was invented in recent years.
Yes.
So thank you for that answer. Now, related to that, one of the questions we had was about the tilt of the Earth's axis, and how does that affect the global energy budget? I mean, aside from the seasons, do you know about that? How does that impact the Earth's climate?
Yeah, so that's a good question, because of course, if you had a perfect sphere, you could roll it around however you wanted to, and the total energy coming in and energy going out would be the same. And so it shouldn't make any difference that the Earth spins about an axis that's tilted with respect to its orbit. But as you see by easily looking at a globe, the distribution of land and water over the ocean, over the world, is not uniform. Indeed, more than 2/3 of the land is in the northern hemisphere, less than 1/3 in the southern hemisphere. And the ratio of land to ocean is 61% ocean in the northern hemisphere and more than 81% ocean in the south. So this has a number of effects. One is water has a very high heat capacity. And so oceans can absorb a very large amount of energy before warming up very much. And furthermore, the land, especially the land in the northern hemisphere, is covered by plants, which absorb energy in the summertime, but it's large fractions of it are covered by snow, which reflect energy in the wintertime. And so it's mostly the asymmetry of the current distribution of continents, which of course is not the long-term distribution of continents. They've been moving around for 4.5 billion years. But the current distribution of continents is such that we get a change in the amount of absorbed and reflected radiation from hemisphere to hemisphere and over the course of the seasons.
So that's interesting. So I mean, this touches, I think, maybe a little bit on Milankovitch cycles and how that plays a factor. Could you maybe elaborate a little bit on that, on how that cycle has played a role in the long-term geologic history of the Earth?
Yeah, so there are 3 major perturbations to the Earth's orbit and orientation that result from the tugs and pulls of the planets and the sun and everything in the moon on the Earth. And they occur on timescales of about 23,000 years, about 41,000 years, and about 100,000 years. So they're very long compared to the timescales we're talking about of 50 years of global warming. But over geological time, they make a very large difference. So the first of these is the precession of the Earth's orbit. So the Earth spins around an axis that's tilted by 22.5 degrees with respect to by 23.5 degrees rather, with respect to the perpendicular to the plane of the orbit around the sun. And because the Earth is spinning, it wobbles like a top, and it does that is points at different North Stars at different times over the course of a 20 to 23,000 year cycle. That's called precession. And because it does that, and because the Earth is in an elliptical orbit around the sun, where it periodically goes closer to the sun and farther from the sun, the combination of those two effects means that at some times in geologic history, the Earth is closest to the sun and the northern hemisphere is tilted towards the sun, that is, it's summer, at the same time. And it's therefore farthest from the sun and tilted away from the sun 6 months later. Whereas today, 10,000 years later, the Earth is closest to the sun on January 3rd, might be surprising to some of you out there, and farthest from the sun on July 4th. The seasons are dominated by the change in the illumination of the sun because of the tilt of the orbit. But there's a slight additional effect from getting closer and farther from the sun by a couple million miles over the course of the year. And because when the Earth is closest to the sun, it's also moving fastest, it means that today we're moving slowly in the summertime, which is why July and August have 31 days and February have 28 days. Summer is 2 or 3 days longer than winter. But 10,000 years from now, we'll be moving fastest in the winter time, in the slowest rather in the winter time. And as a consequence, winter will be longer. And the combined effects, as we can see in the record from the ice cores and ocean sediments, have major impacts on the Earth climate. The third effect is the amount of tilt of the Earth's axis, not where it's pointing in the sky, but whether it's tilted over more or tilted over less. When it's tilted over more, since the tilt is what causes the seasons, that exaggerates the seasons. Summer is a little hotter, winter is a little colder, and when it's tilted over less, the seasons are muted. Now, the total range there is only about 3 degrees, and so it's not a major effect, but it is enough to trigger things like ice ages and interglacial periods such as what we're living in now. So these relatively small effects do have a big effect on climate. And the third is the shape of the Earth's orbit. The Earth, as I say, is in an orbit that's an ellipse around the sun with the sun offset from the center. It goes from almost perfectly circular, only 0.5% out of being a perfect circle, to being 5.5% out of a perfect circle. I'm exaggerating here a little bit, but quite elliptical. And that also has a large impact, and indeed in the last 400,000 or 500,000 years has had the dominant impact because the peaks of glacial periods have occurred when the orbit is most elliptical, and the interglacials occur when the orbit is more circular.
So it seems like the most common question or rebuttal perhaps that people have when it comes to climate change is they point out that we know from the geologic history of the Earth that there were times when the Earth was much colder than it was now and times it was much hotter. So if the Earth's climate changes naturally, then why should we be concerned about climate change?
Well, of course, the creatures that were around when the Earth was considerably warmer and there was 10 times the amount of carbon dioxide there is in the atmosphere today didn't have much of a concept of the future. You know, they were 3-foot dragonflies and large dinosaurs and things like that. And they didn't think a lot about the future. So we shouldn't be concerned if we're just interested in the fact that life will continue to exist on the planet and will adapt to the conditions as they change with time. However, we tend to have a concept of the future. We tend to think not only about what happens in our lives, but what happens to our children and our grandchildren. And as a consequence, we have a different time horizon on which we are concerned. The other point is that up until 50 or 100 years ago, the number of people on the Earth was completely within the so-called carrying capacity of the Earth. That is, the amount of resources we were using was reasonable. In the last 50 years, when we've gone from less than 4 billion people to nearly 8 billion people today, we're stressing the carrying capacity of the Earth significantly, and in fact, using resources at an unsustainable rate. And so while the behavior of humans going back 400,000 years since Homo sapiens first emerged on the plains of the Serengeti had very little impact on the Earth, we've reached a unique moment in the history of the Earth where this one species has produced 8 billion copies of itself and is having a major impact on the geochemistry of the Earth's atmospheres and oceans. And again, if we're only concerned about life of some form continuing, it's not a problem. But if we're worried about the fate of those 8 billion people and their offspring, then it's a matter of serious concern. It's also worth noting that these timescales of massive changes in the average temperature of the Earth and the composition of the atmosphere typically take place on geological timescales of thousands to tens of thousands of years or even longer, whereas here we're talking about a change that's being induced by human activity on the timescale of less than a century.
Those are really good points. So in your talk, the focus of your talk was talking about the ratio of the carbon-12 and carbon-13 isotopes and how those give, that's the footprint that tells us that it is from fossil fuels. And one of the questions is something I've struggled with as well. And that is when it comes to talking about the ratios of carbon-12 to carbon-13, it can be challenging for people to understand what those ratios are actually telling us. Do you have any tips or analogies that you use on how to better explain why those ratios are what they are and how the changing ratios tell us what we know?
So there's a carbon cycle in which carbon appears in various forms in the Earth. It's obviously in the atmosphere in the form of carbon dioxide and methane. It's in the oceans. It's in both the plant life and on the land and the animal life in the ocean. It's subducted deep underground when tectonic plates cover up millions of years of detritus raining down on the floor of the ocean, and it comes out again in the form of volcanoes. For most physical processes, carbon-12 and carbon-13 are treated the same because they're carbon. They have 6 electrons, they have 6 protons, and that makes them carbon, and all carbon is the same. However, the different isotopes, carbon-12, 13, and 14, have different masses, and therefore they move at different speeds. The larger masses moving more slowly, something I've come to recognize with age and weight gain. So the point is that when plants suck carbon dioxide out of the air, which is the first step in photosynthesis, bringing in a carbon dioxide molecule using energy from the sun to break the bond in that molecule, breathe out the O2 so we can breathe it in, and incorporate the carbon into the life of the plant, the cellulose and other molecules that are needed. It discriminates against the heavier, slower moving carbon-13. That means that plant material has a lower ratio of carbon-13 to carbon-12 than the air that the plant breathed in. This also occurs in the ocean. So the algae and plant-like plankton also discriminate against carbon-13 when they breathe in the carbon. And as a consequence, the carbon in the water is enriched in carbon-13 because the plankton are taking up carbon-12 more readily than carbon-13, leaving extra carbon-13 behind. That means the animal plankton, which build little tiny calcium carbonate shells, they use that carbon in the seawater to do that, called foraminifera and various other kinds of plankton. When they die, their little shells sink to the bottom of the ocean and they accumulate there. And those are enriched in carbon-13 because they were drinking seawater or using seawater that was enriched in carbon-13. When that, through the process of tectonics, eventually subducts under a continent and comes up where a volcano is, like the subduction dome we have in the east and the west coast of the US, or the Pacific and right around to Travis's place in Alaska, the zones they're subducting, and there's a ring of volcanoes there. When those volcanoes belch out the carbon dioxide from the molten limestone that came from the bottom of the ocean, it's enriched in carbon-13. So the carbon-13 to carbon-12 ratio of volcanic gases is higher than exists in the current atmosphere. So it's a complex interplay between physical and biological processes that link the carbon as it moves through the whole system that gives you different isotope ratios in different parts of the system.
So it would seem to be simple enough to say that the carbon dioxide released from the burning of fossil fuels is enriched in carbon-12 because that is preferentially used by life. And then the carbon that's released by volcanic activity is enriched in carbon-13 because that is the end result of the carbon that was subducted many millions of years ago. Is that
precisely?
Okay. So related to this, we had a couple comments about the differences between the northern and southern hemispheres. So Deborah posted a question in the chat about talking about how the carbon cycle is much attenuated in the southern hemisphere because of less landmass. So of course, and when we've been talking so far about summer and winter, we're talking about the northern hemisphere, the rockinest hemisphere on Earth, to quote The Simpsons. And so the question is so that we kind of have two questions here, and one is basically are things different in the northern and southern hemispheres as far as carbon usage and also just the circulation?
Well, if I can share my screen here. Oh, I can't. You disabled me. All right.
Here, I will gladly give you access. Hold on. If I can figure out how to do that. Okay. Can you share now?
Yes.
Okay.
Oh, wait a minute. Just a second. So one question was, has anybody done this in the southern hemisphere and produced the equivalent of the Keeling curve in the north? And the answer is yes, they have. And here it is. This is done by the CSIRO, the Commonwealth Scientific and Industrial Research Organization, which is sort of the Australian equivalent of some combination of NSF and the Department of Energy with their own labs. And they started this a little later in 1975, as you can see. And you see exactly the same slope. 1975, we were around 330 parts per million. 2020, we're at 410 parts per million, 411 today. I just looked it up. And you see that's exactly where they are. So there's no difference between northern and southern hemisphere. But you also see these annual wiggles. You see them, but they're much reduced from what you see on the Keeling curve in the northern hemisphere. And that's simply a result of the fact that the southern hemisphere has much less land area and let me do this again here, much less land area covered by plants. So here is the Earth. The green areas are covered by trees and grasses and crops and things like that. You see a gross difference between northern and southern hemisphere. The red and orange are tropical rainforests, and you see there's some in the southern hemisphere, but there's that much there as opposed to all this here. And the yellow is deserts, so nothing grows there. And you see the southern hemisphere has, or dry grasslands, not necessarily deserts, but so you see the asymmetry is enormous. And so the seasonal variation in the carbon dioxide being sucked out of the air by growing plants and then in the wintertime released through decaying bacteria is much more pronounced in the northern hemisphere than in the southern hemisphere. And so that's why this curve looks so different in the north and the south. You can still see the annual wiggles because the same process is going on, but it's much reduced in amplitude because of the difference in the forested and grassland covered land masses.
And is it out of phase? That is, I mean, with the northern hemisphere, so where we see the peaks in the, basically we see the most absorption right now.
Right.
And then for them, it's just the opposite?
It's exactly out of phase, yes, by 6 months.
I'm actually surprised about that because I would think with just the massive circulation that occurs in the atmosphere of the Earth, that pretty rapidly the differences between the northern and southern hemispheres would get smeared out fairly quickly. But I guess the answer is no, that the circulation stays contained enough that the two hemispheres remain distinct.
Well, notice the Earth is rotating like this, right? So the wind patterns are mostly east and west. And while the Hadley cells do turn over the material, the atmosphere from the equator to the poles, that's a longer time scale. In fact, you can even see this in the northern hemisphere. If you look at the Hawaii curve versus a curve done in Alaska, the Alaska curve has a bigger amplitude than the Hawaii curve does.
Oh, that's interesting. I didn't know that. So Deborah had another question here in the chat. She says, in terms of the fossil record and specifically ice cores, how sharp is the CO2 record? So Deborah, by that, do you mean like timescale wise, how precisely can you measure the accuracy of time?
I mean, yeah, exactly, because I would think that diffusion in the ice core would tend to smear that record out. And so I wondered if that diffusion is a correction is applied to account for that.
Yeah, well, there's several corrections you have to make near the top of the core. When you see, once you seal off, so the top of the ice core is called firn material because it's sort of not solid ice. It's sort of flaky. I mean, of course, it falls as snow originally. And so the air that gets trapped there diffuses quite a bit up and down. And so you're smeared out. I believe it's sort of a 50-year time scale or something like that. But once enough accumulation occurs that you seal off the bubbles, then you really don't get much diffusion at all out of the bubbles. The ice is quite dense and it's, of course, quite cold, and it's under quite a lot of pressure. But at the top, you have really nice annual layers, just like tree rings, and you can count them going down. But once you get down, half a kilometer, they're all squished together. So then you have to do more empirical calibration of the age as you go down. And for the top, tens of thousands of years, you can use carbon-14, but you can only use that up to about 50,000 years. And then you run out of carbon-14, so you can't use that for dating anymore. People have tried to use beryllium and various other isotopes, but the production rate of beryllium, like the production rate of carbon-14, is not constant because it's produced by solar activity, either screening out extragalactic cosmic rays from the galaxy or produced by solar cosmic rays. And the activity of the sun over long times is not known, of course. And so there is smearing, yes. But once you seal off one of those bubbles, there's not diffusion out of that bubble into other bubbles. The bubbles really are quite distinct, and you can see them down for a couple kilometers into the ice.
So just a follow-up, which is that we often point to this curve and say, yes, it's true that the CO2 levels have risen and fallen in the past, but right now there's this unprecedented rise, which is greater than anything we've seen before. But that process of diffusion or blurring would tend to bend in time the CO2 level. And so I'm wondering, could it have been actually, there could have been spikes, but those spikes aren't temporally sampled well enough to understand that?
Yeah, I would say spikes on a time scale of decades are probably not temporally sampled enough to see them. But on longer time scales, of course they are. And I'm about to show you here a curve I'm sure you've seen before, but it's such a dramatic curve, it's worth showing again. And so you see the record in carbon dioxide is in red here, right? You see it's got bumps and wiggles, but note the time scale here. This is 450,000 years altogether. So you're seeing things on a resolution of a few centuries at best is the sharpest features you can see in here. And on that time scale, I think there's not a problem of diffusion. On shorter time scales, there is. So here is the, I wanted to show you the right one here. That's where it is today. Mm-hmm. And of course, it's going up with time. Now, it's not true that this is the most carbon dioxide we've ever seen in the atmosphere. This is 400 parts per million. The geologic record suggests that there was 4,000 parts per million during the Carboniferous period 300 million years ago when the fossil fuels were laid down. So there's been much more carbon dioxide in the atmosphere, but not since humans evolved around here somewhere.
So I think one of the important points to make with people is that there have been natural events that have spiked the carbon dioxide. I don't think within a timescale as short as 100 years, but these rapid changes in climate have led to mass extinction events.
That's right.
So,
and there was one time when it was that rapid, and that was the KT boundary, or now it's called the KP boundary, the Cretaceous Paleogene boundary, which saw the demise of the dinosaurs. Then the carbon dioxide did indeed spike, partially because the dinosaurs were unlucky that the meteorite hit the Yucatan in Mexico, which has a very high sulfur content in anhydrite or gypsum. And so that produced a huge amount of sulfuric acid in the atmosphere, which basically led to a nuclear winter, a darkening of the Earth, and then the forest fires as well. So there were big changes in the atmospheric composition on timescales of years when that event occurred. But as you say, it was when something like 60 or 70% of the species went extinct. So yeah, it's not a happy time. Unless you were a little furry creature, which was good for us because that's when the mammals rose.
Yeah, so who knows? Maybe a mass extinction is not a bad deal after all.
Yeah, I tell my students, life is going to go on the Earth for another billion years or so. We're not going to extinguish life. There's no way we're going to do that. Might not do so well for our species, but we're not going to extinguish life.
Yeah, I think that's an important point with the messaging about climate change, is we often talk about saving the Earth, and we don't have to worry about the Earth. The Earth is going to be fine, but it really is save the humans and in particular, the plants and animals that we rely upon. So, I mean, as far as I don't know this very well. Is there evidence that of some of the past mass extinctions that are tied directly to carbon dioxide release, like a supervolcano or any sort of event like that?
Well, as you probably know, even the KP boundary at 66 million years ago corresponds to the time when the Deccan traps in India were produced, which is a massive volcanic eruption, not explosive, but pouring magma out for a couple million years. And that's expected to produce a large amount of carbon dioxide. Most people believe that the asteroid was the coup de grace, if not the total cause of the demise of so many species. But the previous extinctions, including the one, 253 million years ago or whatever, the Permian extinction, corresponds to an even more massive volcanic eruption in Siberia. And it's thought that that may well have been a consequence of a massive change in the atmospheric composition because of the addition of that carbon dioxide and a rapid change in the climate that just wiped out many species. So yeah, there's definitely arguments in favor of large volcanic eruptions changing the CO2 content of the atmosphere and that leading to a mass extinction.
Interesting. So talking about the Carboniferous period, I mean, that is the time in history where coal originated, the coal that we're digging out of the ground and burning now. Do you know how much the carbon dioxide levels would go up in the Earth's atmosphere if all that coal is burned?
As I recall, and I probably shouldn't say this because I can't guarantee that it's true, that we've used about 5%. That might be just the accessible or mineable coal, 5 or 10% of the coal. There's still plenty of coal in the ground. We're not going to run out of coal. For people who talk about peak oil and peak coal, we're not running out of coal. There's plenty of coal in the ground. So it would, I mean, given 200 years, we've burned 5 or 10% of it, and it's gone up by 33% or 100 parts per million. Burning all of it would go up another 1,000 parts per million. It's that order of magnitude, I think.
Mm-hmm. So I think
a significant fraction of the Earth was covered with plants, warm, fast-growing tropical plants in that period, and they all got buried. So it's not surprising that leads to the several thousand parts per million that we've seen historically.
So it sounds like at the very least, it's clear that unless we want to return to a time like the Carboniferous period when carbon dioxide levels were like 4,000 parts per million, that coal has to stay in the ground, that we can't burn it all.
Yeah, and the best way to scare people is to tell them that the bugs had 3-foot wingspans.
Well, for those of us who have lived in Tucson or now live in Tucson, we're familiar with those. I think those are all the questions that we had on the YouTube comments. What other questions from our audience here that anyone would like to ask? And Phil, I'll just say David is an expert on just about any aspect of climate change, and also particularly teaching it. And so if you have any questions you'd like to ask him about, particularly the work he's been doing at Columbia and teaching classes specifically about climate change, something that we astronomers don't normally do, here's your opportunity to talk with an expert.
Yeah, I shouldn't claim to be an expert. I'm an amateur expert or an expert amateur, maybe something like that, because I do not do research on this subject. So but
you're definitely an expert at teaching it. And I think that's something that's very important Because I mean, one of the issues here is just, it's not just simply knowing all the science. That doesn't make us good at helping people understand the issue. So Alexi, it sounds like you had a question, but maybe David, you could, after that, you could talk a little bit about what you do at Columbia and how that, and how, you know, how effective that's been. Alexi, go ahead.
Yeah, I wanted to ask whether in the classes you teach, if there's any experiments, like easy experiments you do to demonstrate concepts, especially for like at the undergrad level. Are there any fun experiments you do?
No, well, the main class I teach is the class that I created here as part of Columbia's core curriculum, which means it's required of all first-year students. So there's 1,150 students in the class, so it's hard to do experiments. And we do this in 20-student seminars, but we get seminar classrooms designed for literature classes, not for science classes. What I do is use, you know, paper kind of exercises and have them work in small groups of 3 or 4. And I use in particular that classical energy balance diagram that shows your 342 watts coming in and it getting divided in various ways and then energy flowing out again. And I have a long series of questions that can take up several class periods of students first understanding the energy balance and seeing how things change, and then incorporating the very important factor of feedback loops by changing one thing and then having them follow it through all the other changes that it can do. I thought of having this made into a computer simulation so you could just push buttons. And I decided that would be less effective, actually, than having them work out on a piece of paper. I use a lot of the Nebraska simulations in my astronomy classes because I find them very useful. But I don't know if I'm not thinking about it right or not, but I find the fact they have to struggle with this one diagram that's in front of them and figure out how changing one component of, say, the evaporation from the oceans is going to also increase the clouds, which increases the reflected light, which decreases the temperature, versus it was going to rain more, so there were going to be more plants, and that would draw CO2 out of the, you know, and they have to worry about all these things going on at the same time. That working it out by drawing their own little diagrams and things like that might be more effective than pushing buttons on a computer to see what happened. We also use the IPCC reports extensively and have the students really come to understand all the graphical representations in there and how one draws conclusions from them and what the uncertainties are. The uncertainties are really important to get across because we're not, you know, we're not religious about this, we're scientific about this, so we don't have absolute beliefs. We have contingent beliefs that are based on the best available information and modeling that we can do, but we're always building models. We're not actually recreating reality, and I make that distinction clear throughout what I do. My talks have every slide labeled with one of 5 labels, either a fact, and to avoid epistemological argument, I define a fact as a measurement of the material world done with the best available instrumentation with an assigned uncertainty, because no measurement is perfect, that's been vetted by peer review or preferably reproduced independently. That's what I call a fact. And then there's physics, which is the model we make to put these facts together and to try to explain them. But it's a model of the world, the most successful model humankind have ever come up with, but it's still a model of the world, not the world itself. And then feedback loops, and then fictions, and then foreshadowing. So I label every slide so it's clear what's the result of a model, what's actually a measurement of the real world, and what's the result of a prediction from a model, which is, you know, perhaps foreshadowing, but far from absolute. And I always use the quote from my late Senator Daniel Patrick Moynihan, who said, "You're entitled to your own opinions, but you're not entitled to your own facts." And so that's how I distinguish the facts.
That's funny. It seems like with climate modeling, I mean, the biggest amount of uncertainty, if you want to call it that, is just simply human behavior. That, you know, there's all these other factors we don't know very well, but it's just simply how we're going to respond to this is the dominant source, and what path our future holds.
Yeah, I would say that there's modeling and there's predictions about the future. I'd say you're right about predictions about the future. It's what are we going to do in the next 50 years? And I haven't a clue, because I'm not a sociologist or an economist or a psychologist or a political scientist. So I have no clue. But the modeling itself is limited by the nested feedback loops, by the fact that there are dozens of feedback loops that are both positive and negative simultaneously and that are nested inside each other. And that's by far the biggest problem. The other problems, like the resolution of the models, you know, whether they're 100-kilometer pixels on the Earth or 50-kilometer pixels on the Earth, that just gets better with time as computers get faster. But that doesn't, computers getting faster doesn't solve the nested feedback loops problem. There are some other particular uncertainties. Cloud formation is a big uncertainty. Aerosol production and the effect of aerosols, because some of them are absorptive and some of them are reflective. Those are things that we could measure better, and people are getting better at it. But the real biggest uncertainty in the models themselves are the nested feedback loops.
Interesting. So we have Ellen has a question, and we have two hands up as well, Jeff and Adrian. So Ellen asks, if only 5 or 10% of the coal has been mined, what about petroleum? What percentage of petroleum has been drawn up? And since that also corresponds with the extinction of animal life or plant life in the past, do you know the numbers on, I mean, I've heard living in an oil state, we talk about peak oil all the time. Have we crossed it? Do you know where we are as far as petroleum, remaining petroleum?
Now, if you'd asked that question 10 years ago before fracking, you know, you would have given one answer that we were really near peak oil, but now we see oil coming out of the ground in ever greater amounts. I believe it's true that the amount of oil available, the fraction of oil we've used is greater than the fraction of coal we've used. And they actually come from somewhat different periods. The coal was laid down in the period about 300 million years ago for the most part. And the oil comes from more like 150 to 200 million years ago. So, but still geologically long ago, it doesn't matter. But yeah, I think at least of extractable oil, I think we've used more than we have of extractable coal. But the total amounts are not well established. And as I say, 10 years ago, before these innovations in drilling, we would have said we were much closer to peak oil. I'm hoping that we sort of never reach peak oil, that we sort of wean ourselves off this and leave some of it in the ground.
So Jeff and Adrian, I don't apologize. I don't know which of you raised your hand first. So Jeff, I'll give you a chance if you'd like to unmute your mic. If you have a comment or a question you'd like to ask, please go ahead.
Sure, thank you. So one quick comment with the energy usage is we're probably going to be limited by energy return on energy invested. So the amount of work that you're having to do to pull that oil out of the ground is rapidly approaching the point of you're using as much energy as you get out of that oil. So, and that's why we're kind of seeing this big collapse in parts of the oil industry at the moment. I mean, it was already in process, and the pandemic has just accelerated it. But on this issue
sort of like nuclear fusion, right? The amount you have to put in more energy than you get out so far, at least.
Yeah, and so then back to this issue of the models, right? And having students go through this modeling. One of the questions that always comes to mind for me is that you know, this is radiative transfer, right? At the most basic model is to just do a radiative transfer model. And so, you know, as astronomers, we do this with Mars, we do this with Venus. And so even just those most basic models show more CO2, warmer planet. And so how wrong would we have to be? Like, how much would we have had to have messed up in our determinations of, you know, the absorption coefficients or whatever for all of this CO2 to not be the cause, right? How big would our errors have to be in measuring the temperature of Mars, measuring the temperature of Venus, right? Because basically whenever I hear some politicians saying that climate scientists are liars, I feel personally attacked because it's the exact same skill set that I use for looking at Mars and for looking at Venus.
Well, I don't know quantitatively, but obviously they'd have to be very wrong, right? Because I assume you get a temperature that's pretty close to the temperature of Mars and pretty close to the temperature of Venus. So yeah, I think that when people, so the worst people are those that deny the facts exist, right? And then the next worst set of people are those who deny that we actually understand anything about the way, as you say, basic radiative transfer and electromagnetic radiation and molecules and atoms work. They're perfectly happy to rely on their cell phone because they believe we know that, but we don't know how to do radiative transfer. It's just very difficult to argue with those people.
It's a it's a tough argument to have. I mean, it seems like a very reasonable thing to say. If we're going to make such radical changes to our economy, shouldn't we know 100% certain before we make these decisions? And on the surface, it sounds like a reasonable argument. And I don't know if this is an effective counter or not, but I think it's analogous to saying, well, how certain are we that the Earth is round? I mean, shouldn't we still be having an earnest discussion about the possibility that it could be flat? And I don't remember who it was, but someone I saw heard recently said, we understand climate change better than we understand cancer, and no one is running around pretending that cancer doesn't exist or that it's some sort of conspiracy. And I don't have any evidence for the effectiveness, but I think these are things that can maybe help people understand how well we do understand it.
This is my favorite cartoon in that regard.
Yeah, that's a brilliant one. Adrian, you had your hand up as well, so I wanted to give you a chance to ask your question.
Sure, thanks. So first, this was extremely interesting and helpful, David. And I noticed at the very beginning of of the webinar, you made a comment, and I don't remember the details actually, about the term climate change. And I was curious, when you communicate about this phenomenon, what terms you like to use and what you found effective in communicating about this. We use this term, whatever we use over and over and over, and so it has some cumulative effect on people's thought about it. So I'm curious about your thoughts about that.
I don't remember if I went into the whole story in detail, but the original paper on this by my recently deceased colleague Wally Broker called it global warming, because, as has been pointed out many times, the climate changes all the time, and it's changed much more dramatically in the past. And in 2002, Frank Luntz, a Republican operative and pollster who is active in this campaign as well, wrote a memo to George Bush saying that we have to make the scientific uncertainty the principal centerpiece here, because if the public believes the science is solved, then they'll solidify their view. And so we cannot use global warming anymore. We have to use climate change. And that was a very influential memo, which clearly worked. And for reasons that I don't fully understand, all the climate scientists adopted it. And I think that was a major mistake. So in my talks, I always call it global warming. I don't call it climate change, because that's the problem. Climate change is not the problem. Global warming is the problem. And rapid global warming is the problem.
Are we playing into their hands by, I mean, I've heard a complaint about, as scientists, we're focused on the uncertainty. We tend to, over discuss the error bars, because that's what we care about, right? We want to know how well we know things. And I've heard from journalists complaints that because we focus so much on the uncertainty, it gives the impression that we really don't understand things very well, and that might play into that denier playbook of saying, well, we really don't know what's going on. Has that been an issue, do you think?
Yeah, I think it's a major issue, and it's almost a philosophy of science issue. The first big mistake we made was calling them error bars, because they're not errors, they're uncertainty bars, right? But the fact that, and we can't resist, I mean, I can't stop myself saying it because I've learned it, for 50 years. So we call them error bars. That's the first mistake. We should call them uncertainties, which is what I did in my definition of a fact. And secondly, we have to, I think, because it would be intellectually dishonest to do otherwise, admit that we are different from, say, let's take religion as an example, where belief is important. We're not interested in belief, we're interested in understanding. And that's different than belief. And so science is not a system in which we try to develop absolute beliefs. It's a system by which we go about building ever more accurate and more predictive models of the material world. And it doesn't go beyond that. So it doesn't say what we should do politically or economically or psychologically in any other way. It just is attempting to understand the way physical processes work and to predict them, because prediction makes one's life easier, right? And I don't think there's a way around, an intellectually honest way around that. And therefore, I would never argue that we know the model for the climate and we run this model and we know what will happen in the future, because we don't. And I think we just get ourselves in trouble when we do that.
That's a good
Reminds me of
point.
another question I have. Can I mention it?
Go ahead.
Which is, there is so much pressure on climate scientists about all of this. I wonder, and I have a certain fear, whether the pressure is such that, there's always uncertainties in our in modeling, and whether there's been, whether there's any way in which climate scientists succumb to, like, oh, let's not, show the model that shows things going really, really crazy, that we somehow are seeing, and like I said, this is maybe just a fear on my part, somehow seeing the more optimistic scenarios, and the scariest scenarios are somehow maybe not being included always, because of this incredible pressure on climate scientists. Do you have any thought about that? I'm curious.
I don't think there's a big systematic bias. I mean, recently this has been discussed in terms of sea level rise, right?
Mm-hmm.
Whether the sea level rise we expect is 0.5 meter or a meter or a meter and a half by the end of the century. And there are people who are arguing that we have underestimated, by saying it's 0.5 meter or something, say, we've underestimated it. And, that's true. We could have underestimated it. But you need to, I don't think the models are up to being able to predict to within 10 or 20 centimeters what the sea level is going to be rising 80 years from now. We can't do it. And so we shouldn't pretend that we do it. I'm not aware from the people I talk to that do this modeling that they're systematically underestimating things. I don't think that's the case.
That's good. And that one other fast question related to this. Do you know of examples where past predictions have been compared closely to what has happened? So, we could say, look, forget the future for a minute. Let's look at the past. We've been making predictions for quite some time now. It'd be really nice to show a plot that's like, here was the range of predictions, and here's what actually happened.
Jeff seems
kind of strengthen, that the argument that predictions actually are meaningful.
Well,
useful.
My favorite example is Wally Broker's paper, who said in 1975, a year where we were exactly on the 20th century average temperature, that in the near future, the increasing carbon dioxide would raise the temperature such that by the second decade of the 20th century, it would be higher than it had been in the last many thousand years. And, that's not a highly quantitative statement, but it's a statement in a paper in Science in 1975. And he was right, exactly right. But Jeff seemed to know of an example of this. Were you nodding your head, Jeff, that you know of an example?
Yeah. So if you remember, a couple of years ago, there was, I forget the journalists, but they won all kinds of prizes for their investigative journalism on this issue of, like, oil company executives' knowledge of climate change. And that included a memo that was presented to Exxon executives somewhere around 1980, and it has a plot of their scientists' prediction of temperatures and CO2 levels, and it is spot on to today.
Well, that's a perfect example.
Yeah, I show this to my classes. I'm just like, here you go. Oh yeah, I'll dig it up.
Send it around. Yeah, that would be great.
Yeah, and I was thinking of that too. The Exxon had very good climate science research going on back in the 80s. In fact, as good as anyone else in many ways. Deborah and Katie, you both had your hands up, and we have about 5 minutes left because I want to be respectful of David's time. So why don't you go ahead with your questions? And Deborah, why don't you go first?
I'll just go very quickly. I'm just wondering how much time to spend on this in my astronomy classes. I typically spend about a week talking about climate change. And so I like the model that you have for teaching science at Columbia, but I was looking for a syllabus and couldn't really find an exact syllabus of the Columbia program, Frontiers of Science program. How much time do you spend on climate change in that class, and do the topics rotate?
Yeah, the topics do rotate. We do 4 topics a term, so it's 1 month a term. 1 month a topic. And there are always 2 life science topics and 2 physical science topics, and one of the physical science topics is always climate change. So it's typically 3 hour-and-a-half lectures, an hour of question of the lecturer, and then a 2-hour seminar for 3 consecutive weeks.
That's quite a bit. And Katie, you had a question as well?
Yeah, this is almost more of a comment. Your talk, of course, David, was excellent and very clear, the way they always are. I was noticing that it was touted as you know, for a more sophisticated audience. I'm trying it out on my 14-year-old grandson, who admittedly is a bit of a nerd, but I think a talk, especially like this one, would be just fine for a lot of younger kids who are interested. And I want to play this game with some of the kids I have available at my disposal. See about that, because it's a beautiful job and convinces people that they understand more than they really do, but that's okay.
It's better than the opposite, right? Yeah, no, those slides are taken from a public talk I did. I modified the language a little bit more sophisticated than I would for the public, but I have versions ranging from 45 minutes to 2 hours of public talks that I give on this. And
yeah, I think somebody was asking whether the slides were available. That might be something else that could be addressed.
Yeah, Mashi asked that question. So
I can send both those slides, but I can send the whole 2 hours if you want. 200, I have 200 slides, and it's divided into 8 chapters, so you can pick which chapter you want to think about the astronomical issues, or the proving CO2 comes from fossil fuels, or what the temperature history is, or something like that. Yeah, I can send them to Travis if you want.
that would be wonderful. I know that people would love to have that. I would too. So
they don't get posted on the web. That's because I made that mistake many years ago and found them being used on denier websites. And so you have to be careful. My slides don't have many words on them is the problem. They're mostly graphs and pictures and images. And they can be misused.
Well, so as far as how to get the slides, David and I will work together on arranging a way for slides to be available to A4E members in a restricted way. And then we'll send out a message to Groups IO so that everyone who's an A4E member can have access. Is that okay, Dave? Would that work with you?
Yeah, as long as they, as I say, don't end up wild on the web. I also have, I wrote a book a few years ago, and one of the chapters, the book is it's called The Survival Guide to the Misinformation Age. So it's about misinformation and how to avoid it. But the chapter in which I sort of tie together all of the scientific habits of mind uses my lecture on climate as an illustration of scientific habits of mind. So I can send you that chapter too, if you want.
That would be great. Well, it is 11 o'clock here in Alaska, and it's been an hour. So I want to thank you again, David, for taking the time to meet with us, and thank you all for attending today. It's great to see you all, and thanks for your questions. And just for those who weren't able to attend, we will be posting this video on YouTube so that it will be available for people, for A4E members as well.
Great.
So thank you all for coming today. Thank you, David.
Thank
And
you.
I look forward
Thank
to
you, David.
Bye-bye.
talking with you all again soon. Bye-bye.
If you're interested in Astronomers for Planet Earth, you can learn more at our website, astronomersforplanet.earth, and on social media as well. If you would like to be notified about future talks and events, please follow and join us.